Hello and welcome back. In this video, I'm going to give a kinetic theory description of an ideal gas. So when we say kinetic theory, just think of it as we are going to have a bunch of marbles rolling around and try to use that as a model to describe things, where we keep track of the collisions and things like that. So we're going to assume that there are capital N particles in a box which collide elastically with the walls. So that means the energy is conserved in those collisions. And we're going to furthermore assume the molecules don't interact with each other. Molecules are, really you could take them to be point-like. And don't interact. So that means that the only interaction the molecules have are with the walls of the box. And okay, so that's pretty much the only thing we're going to assume at the outset. I think is there anything else? Oh, the other thing we will do is we're going to assume no preferred direction. You'll see where this enters later on. So that means that the molecules don't, when they're floating around inside the box, they don't care up versus down, right versus left, front versus back. They just move around at random. Okay. So what we're going to do is, let me first draw a picture of this. Okay, so the picture we're going to have is, let's say there's a box. And what we're going to do is, okay, let me kind of dot in there the back bit, the part that's hidden behind. Okay, what we're going to do is shade in and imagine a certain little zone here. So I'm going to go ahead and kind of sketch it in here. So think of this as kind of like a slice of bread there at the end of the box. All right. All right. We're going to go ahead and say, or assume, that the area of the face here is capital A. And I'm going to let this little slice of bread, for lack of a better word, have a width delta x. And we'll see how I'm going to use this idea. All right. So, and I'm also going to assume all the molecules have the same mass. You can easily generalize it to account for other situations. All right. So we're going to try to develop an understanding for where the pressure acting on the face of a box could come from. But what we're going to do is, well, it's no surprise, it's going to come from molecules or these little marbles or whatever bouncing into the wall. So what we're going to do is account for this kind of in a certain particular order it's not the only way. I've seen lots of other discussions of this. You always get the same answer, but you need to kind of organize your thoughts so that you count everything once and you don't want to count it, you don't want to overcount the effect. So what I'm going to do is first, let's put the steps here. Consider one molecule collision with velocity, and I'm really talking about the horizontal velocity, but I'll just say Vx if I'm talking about this is the x direction. And then, so that's step one. Step two, consider all molecules with the same velocity in the x direction. And then step three is, so this is, you pick one molecule with one velocity, then you consider all of its cousins with the same velocity, but maybe distributed throughout the volume somewhere. And then finally, to get the total pressure, we're going to count or consider all velocities Vx. And by the time we do that, we will have accounted for all possible molecules with any possible velocity. That's everything. All right, so that's going to be our strategy. It's just a way of organizing our thoughts through this. Okay, so if you think about it, imagine, so let's do one molecule. If we have a wall and the molecule is here with a velocity that's before, and I'm really only concerned with the perpendicular velocity. The longitudinal components, the other x and y components, play no role in this discussion for right now anyway. What I know is that when this molecule comes in, it hits the wall at some point. Kind of mark that point right here. And then that's kind of my collision point. And then it's going to reflect. And I'm going to have, do the next one in green, I guess. After the collision, I will have that molecule going in the opposite direction. Because energy is conserved, what I know is that the velocity after the fact will just be this equal magnitude, just reversed, just flipped. Okay, so that's kind of an interesting little thing. Now, just like in physics 1, to discuss collisions, I want to look at momentum conservation. So I'm going to say that the change, let's go back to black here. The change in momentum in the x direction, well, that's just going to be the mass times the change in velocity in the x direction. And since they have equal magnitudes, just opposite directions, this is actually equal to minus 2m times the initial velocity. Because the final minus initial, there's a double negative and you end up with a doubling effect. So this is a momentum, this is the change in momentum of the molecule. Now, so this is the change in momentum of molecule. And we saw in physics 1, that means, oh, okay, take that before I move on. That's the change in momentum of the molecule, but if you turn it around, that also then becomes, if I include the wall as part of the system, that becomes minus the change in momentum of the wall. So I find that the change in momentum in the x direction of the wall is simply going to be the opposite really just using Newton's third law, plus 2mvx. So this is every little collision is going to impart a little bit of momentum on the wall using the impulse momentum theorem, or, well, yeah. We saw that in physics 1 that this is simply going to be the average force during the collision times the time it takes for the molecule to collide. So, and this really, I should do an integral here, but as long as the collision is very quick, this is a good approximation. All right. So turning that, just kind of summarizing that, I find that from the force due to one particle with one single velocity, Vx, the average force in the x direction equals, actually I'll just write force times delta t equals 2 times m times the velocity of that particle before the collision. All right. I should also look, I'm only looking at particles, well, in order for the particle to even have a chance to hit the wall, it had to be moving to the right. Okay, so that's kind of implicit in this discussion. Very good. So that we dealt with one particle. Now we need to look at all with the same velocity, Vx. So just kind of going through my list, kind of considering these. We handled one collision. Now we're going to do all collisions with the same velocity, Vx. And now I kind of need a number here. So what I'm going to do is I'm going to say, well, first off, let's say, and actually, you know what? Let's put a label here, because eventually we're going to consider all of them. So I'm going to label this velocity with an I. So I'm going to say there are n sub I molecules with velocity Vxi. And in this, if you want this kind of tissue box shape, I'm going to assume that these particles are evenly spread out, that there's nothing special about any direction or any place. It's just all equally likely. It's an assumption, but it seems like a reasonable one. And what that means is that I could actually define, or it might be useful to define, a number density, not a mass density, with velocity of particles with that velocity. And I'm going to call that Ni over the total volume. So that would be the number with velocity Vxi or per volume V. Now, why would that be a useful concept? Well, the idea is, remember, densities are useful for turning kind of physical quantities into geometry kind of quantities. So, or relating physics and geometry. So in this case, we have these particles with this all with the same velocity, and they just happen to be in different places. And we're going to assume they're more or less evenly spread out. Now, what's going to happen is only the particles that are near the wall have any chance to hit the wall. So there could be a particle over here with the same velocity moving to the right, but in time delta t, it'll never reach the wall and therefore cannot contribute to the pressure. So what we're going to do is basically just say, the question is, how many particles or how many collisions, I can spell, how many collisions are there? Well, it would be the volume of, And so what I want to do is say, well, okay, so here's my tissue box. If I choose the width of this slice of bread here on the end, so if I look at delta x and I set that equal to Vxi, so I should put a label I on delta xi, times delta t, then any particle with this velocity that's inside the slice of bread will hit the wall. Any particle that has that velocity but is not inside that slice will not hit the wall. So for counting how many collisions with the wall, basically what I want to do is figure out the volume of the slice, multiply by the velocity density, and then calculate, and then the change of momentum of each one. So the change of momentum for the wall is going to equal, well, you could be the number of collisions with particles with that velocity times delta p for each one. The number of collisions times the change of momentum from each one, but that's simply going to be the volume of that. So that's going to be the area times delta x with that label I, that's the volume, times the density. We said that was the total number in the entire volume over the total volume times the change of momentum coming from one such collision, which was 2 times m times the velocity Vxi. Now, using my formula for the width of that is related to the velocity, I get that this is the area times delta t times the velocity in the x direction times the number of particles with that same velocity in the entire volume over the total volume times 2m Vxi. Oh, well, look, these are the same. So I could just regroup that a little bit. I can write that as an area times delta t divided by a volume times a number with that velocity times the x velocity squared. And then I have to multiply by 2m. Awesome. So that means so this is the total change of momentum coming from the particles with that same velocity. And I can rewrite that using the impulse momentum theorem as the force average from particles with that velocity times delta t using the impulse momentum theorem, as I mentioned before. And then I can simply divide by delta t. And you can maybe kind of see where I'm going here. I'm writing that's the average force from that velocity's contribution over the area, times the volume equals the number of particles with that velocity times Vxi squared, and I have a 2m sitting here still. All right. Now, when I was doing this, I was only kind of implicitly summing over things which are moving to the right. What I could actually do then, oh, okay. So then I can extend this, instead of having a right-bound sum over all velocities, I could extend this to a sum over right and left. That kind of overcounts the velocities. So I would have to divide by half. So what we're going to do is as follows. We're going to basically say that the total force on the wall over the area, that's just going to become pressure, times the volume would be the sum over all right moving labels I of, and I would have the number of times each one occurs times 2 m v x I squared. That gives me the total force on the wall due to collisions with particles with any possible right moving velocity. And if I wanted, instead of having right moving only, now I can just extend this to be all velocities as long as I cut the result in half, because I would be overcounting. And when I cut it in half, the 2 goes away. And I get the sum over all velocities I, the number of particles with each velocity, times m times vxi squared. And we're almost done. On the left-hand side, this first factor is pressure. The second factor is volume, as is obvious. And what I want to do is multiply and divide by the total number of particles in the entire box. I can do that. I've just multiplied by 1 in a clever way. But then this looks like the probability of having the ith velocity. Which means I can write this as the number of particles and times the mass times the average x velocity squared, because it's the probability of Vx squared. So this gives me my first formula relating pressure to something about the particles inside the box. Now, I'm going to make use of an assumption I already stated. If x is treated the same as y is treated the same as z, as far as the molecules are the same, then it should be true that Vx squared equals Vy squared equals Vz squared, which must be the same as 1/3 of Vx squared plus Vy squared plus Vz squared, otherwise known as 1/3 the vector velocity squared. Remember, V vector squared is V dot V, using the dot product. So I get the following interesting formula. I can write this as P times V equals the number of particles times the mass of each particle times 1/3 the average of the vector V squared. And now I'm just going to massage it a little bit and say this is 2/3 N times the average of 1/2 mv squared. Notice this is nothing other than the kinetic energy per particle. The average kinetic energy of a particle. So this gives us a nice, kind of neat little formula. It relates pressure and volume in an ideal gas to some numbers times an average kinetic energy per particle. This thing, on the other hand, one of the ways that we wrote the ideal gas law was to say that P times V equals the number of particles, and this is the physics way of writing it, times the Boltzmann constant times temperature. But comparing coefficients, what that means is that temperature must simply be, it must be that Kb times temperature is nothing other than 2/3 times the average kinetic energy per particle. So we learned that the interpretation of temperature in the ideal gas law is that it is the average kinetic energy per particle in an ensemble of molecules rattling around inside the box. So that kind of meshes with our intuition. Somehow when things have high temperature, they're very energetic, but this is sort of the microscopic kinetic energy that each little molecule has at its disposal. That gives us the interpretation of temperature for an ideal gas. All right. I think I'm going to stop there. I might post a video on the actual way, kind of the probabilities of different velocities. We'll see. But this sort of closes the loop as far as what we needed for this semester at this point. So catch you next time.